Hello and welcome to another video of class 12 physics chapter 1 electric charges and fields, and this is part 4 of this series. Okay, today's topic of discussion is Coulomb's law. Okay, uh, so far we have discussed charge, its properties, and uh, one important information that charges attract or repel each other. Okay, charges attract or repel each other means they exert forces on each other, right? When we say attraction or repulsion, it means there is an idea of the direction of the force, in which direction they are exerting forces on each other. Okay, only the direction, idea of the direction is there, but there is no calculation of the amount of force exerted by the charges. We don't know the force is of 100 newton or 150 newton or 200 newton. Okay, we are unable to calculate, right? In order to calculate the amount of force exerted by the charges, uh, Charles Augustin de Coulomb has given a law known as Coulomb's law, and according to him, charges exert forces on each other known as electrostatic force of attraction or repulsion. This electrostatic force of attraction or repulsion is directly proportional to product of their charges and inversely proportional to a square of the distance between them, and the force between those two charges always act along the line joining the two charges. Okay, this was the statement, and according to this statement, we can formulate an expression. Using that formula, we can calculate the force between the two charges. On your screen, the statement is written, and kindly note it down. It says the electrostatic force of attraction or repulsion between two static point electric charges is directly proportional to the product of their charges. Okay, this is the first point, right? The first point says the force between two static point charges is directly proportional to product of the charges, and the second point says inversely proportional to the square of the distance between them. The point number 2 is the force of attraction or repulsion is inversely proportional to the square of the distance between them, and this is the point number 3, which says the force acts along the straight line joining the two charges. Okay, these points can be simplified with the help of diagram. Let us see the possible cases, right? We use certain symbols which can be commonly used. See, if 2 point charges q1 and q2 are separated by a distance r, q1 q2 are the two charges and the separation between them is r. Okay, and let F be the force, electrostatic force acting between these two charges, right? The force symbols used are q1, q2, r and F, right? We have two charges, and two charges can be both positive, can be both negative, or they may be dissimilar, one positive, one negative, right? There are many cases. So one by one we discuss the cases. See here in this diagram, there are two positive charges q1, q2, and the separation between them is r. right? Separation between them means from the center of the first charge to the center of the second charge, the distance is r, right? Okay, since these two charges are similar, they repel each other. There are force of repulsion between them, they repel each other. And you can notice the direction of the force is along the line joining the centers of the two charges, right? The statements contains this part also, that the force always acts along the line joining the centers of the two charges. Okay, uh, one more point you can notice here, they attract or repel each other. Okay. The stress should be given on each, the word each. It means Q1 repels Q2 and Q2 also repels Q1. Okay. Do you remember Newton's third law of motion, which says for every action there is equal and opposite reaction? Okay. It is also applicable here. If Q1 applies a force of 10 Newton on Q2, then Q2 also applies a force of 10 Newton on Q1. Okay, so these two forces on Q1 and Q2 are always equal. 10 Newton, second is also 10 Newton. And about the directions, when you compare the two directions, you can see that they are acting on two different objects and two different directions. You can see here in this diagram, suppose this force is along right direction. What about this force? It is along left direction. Suppose this force is of 10 Newton, then this force is also of 10 Newton. You can give a different name. You can give a different name like F2 on 1, F1 on 2. Sometimes we write F21 like this. Sometimes we write F12. It doesn't mean, it is a name, okay, given just to recognize what we are talking about, which force, right? It is just for the recognition purpose, but in magnitude they are always equal. This force and this force both are always equal, right? Okay, I think it's okay now. Okay, next case you can see is about two dissimilar charges. Right now here there is a negative charge and a positive charge. Obviously there is an attraction and the attractive forces are given names, F2 on 1, F1 on 2, right? किस पे लग रहा है, कौन लगा रहा है ना, it is mentioned in the symbol so that you can easily recognize the force, but the forces are equal in magnitude, right? And the distance between them is r. Distance between them means what? From the center of the first charge to the center of the second charge, the distance is measured as r. Okay, clear? The possible cases are all listed here. And now, according to Coulomb, the force is directly proportional to product of charges. Okay, we have given the name charges as Q1 and Q2. The force of attraction or repulsion between the charges, okay, is directly proportional to product of their charges. So F is proportional to Q1 Q2, and the statement has second part that says the electrostatic force of repulsion or attraction is inversely proportional to a square of the distance between them. This second part is also called inverse square law. Do you remember Newton's universal law of gravitation taught in class 11th? The same type of a statement is given by Newton's universal law of gravitation, that says the force between two masses is always attractive, 1 point, and this force is directly proportional to product of their masses and inversely proportional to a square of the distance between them. Both the laws are similar to each other. The only difference is they are between masses, and right now here the charges are there, right? So this becomes F equals to Q1 Q2 by R square, and this K is a proportionality constant, right? This K has a lot of things, it contains a lot of things we will discuss later, but right now you can say this K as a proportionality constant. Okay, so it becomes K Q1 Q2 by R square. Okay, now this is another statement. The formula can be expressed in a different manner. We have used modulus sign. What is the purpose of this modulus sign? We have to take charges as magnitude only. What is the meaning? We have to put the values of the Q only and just leave the sign. Suppose we are having two charges, one is 10 microcoulomb, another is minus 10 microcoulomb. So negative doesn't required here, just put 10 and 10. Okay, whatever is the value only you have to put the value. Okay, so this force gives you the magnitude of the force between the two charges. This force doesn't have like this, vector sign is missing here, not given. So only when we write only F, it means magnitude of the force. Okay, clear? Okay, so finally what is there? We have the K, the constant. About the K, see here, this constant K is equal to 1 by 4 pi epsilon naught. Okay, we will discuss this part later, but right now you just remember this K is a constant and it is equal to 1 by 4 pi epsilon naught, and by putting the value of epsilon naught, which is equal to 8.85 into 10 to the power minus 12 Coulomb square per Newton per meter square, you will get this much, 9 into 10 to the power 9. Okay, clear? In this formula K equals to Q1 Q2 by R square. In this formula, this K is always substituted by this value, provided the charges are kept in air or vacuum. Mind it, right? This K depends upon medium in which the charges are kept. But when nothing is mentioned, where are the charges, in which medium they are kept, just assume that charges are kept in air or vacuum, right? In those cases only you can take K as 9 into 10 to the power 9 Newton meter square per Coulomb square. Okay, this also gives you one question mark. What will happen if the medium is other than air or vacuum? Okay, this part we will discuss with the topic permittivity of a medium. Okay, in next part, right, part 5, right? Till then we just assume that charges are kept in air or vacuum, and we have to take this K as 9 into 10 to the power 9 Newton meter square per Coulomb square. Okay, this constant K is called Coulomb's constant or electrostatic force of constant. Okay, we read this symbol as epsilon naught. It is called permittivity of free space, right? Permittivity of free space. We have to discuss it in detail, okay, in the later part, right? Okay. So the next part is some important points regarding the Coulomb's law we have discussed just now. What is this? This is the law is based on physical observations and is not logically derivable from any other concept. Sometimes you have seen that we have derived gravitation's law, Newton's universal law of gravitation from Kepler's laws of planetary motion. Okay, in class 11th, in the chapter of gravitation, you have been taught like that. But in case of Coulomb's law, you can't say that the Coulomb's law can be derived from some other law or other concept. Okay, experimentally till date it is okay, it has it is not violated. Okay, next. Now we are going to compare Coulomb's law with Newton's universal law of gravitation. Okay, there are 3 points of comparison. One is this formula, we have already discussed that this is very similar to Coulomb's law. This is Newton's universal law of gravitation, and it is very similar to K into Q1 into Q2 by R square, right? So they are very similar, but there are differences too. What are the differences? Point number one. Point number one says electrostatic force is very large, or you can say it is much stronger than gravitational force. Okay, electrostatic force is huge in comparison to gravitational force. Clear? And the second point is gravitational force is always attractive, but electrostatic force can be repulsive, can be attractive both, but gravitational force is always attractive. Point number three is gravitational force doesn't depend upon the medium in which the masses are kept. Suppose moon is there, earth is there, in between there are medium, there is no medium. Okay, but it doesn't matter, medium doesn't matter in the calculation of gravitational force between two masses, but in case of electrostatic force it matters in which medium the charges are kept, right? So these are the 3 important differences between gravitational force and electrostatic force. Okay. Some limitations of Coulomb's law. Coulomb's law is also limited. Okay, Coulomb's law is applicable in case of charges are point charges. This law is applicable only for the point charges and should be at rest. 2 point charges, they are static, they are at rest, then you can apply Coulomb's law to calculate the force between them. Point number 2, regarding inverse square law. Wherever the inverse law is obeyed, only then you can apply Coulomb's law. Okay, clear? Third point is, it is difficult to implement Coulomb's law where charges are in arbitrary shape. Suppose one house is there and charge is on it, okay, some different shape, some arbitrary shape, right? So it is very difficult to have to calculate the distance between such two objects, right? So we cannot apply Coulomb's law. Coulomb's law is always applicable where the charge on an object can be supposed to be a point charge. And what is the important condition for a point charge? The important condition for a point charge is the distance between the two charges should be very high in comparison to their size. Okay. Next point is, the law can't be used directly to calculate the charge on the big planets. Okay. This law cannot calculate charges on planets. Come on, we just give you an idea about some calculations where mistakes we commit. In order to avoid such mistakes, we must recapitulate the concept of vectors and its magnitude, its direction, right? See, here on the screen there are 2 examples, right? Both is from Newton's second law of motion, F equals to ma. But in the first example it is written in vector format, and in second example it is written without vector sign. Then what is the difference between these formula? In both the formula you can put the values of mass and acceleration. Okay? and you can calculate the magnitude of force, right? Put the value of m and a, you will get how much force is there. You can get 100 Newton, you can get 200 Newton. The magnitude of the force is calculated, right? But the first formula contains vector sign, means it contains direction along with the magnitude. Okay. In second case, it is only about the magnitude of the force. 100 Newton is calculated, done. The work is over. Only magnitude of force. That's it. F equals to ma without vector sign. That's over. It is only asking, or you can say this formula can calculate only the magnitude of the force. Similarly, we are having the formula given by Coulomb's law as k q1 q2 by r square. F equals to k q1 q2 by r square. It doesn't contain any vector sign, right? So this formula gives you the magnitude of the force between two charges only. It doesn't give you the direction of the force, right? You have to put the value of k, q1, q2 and r, and the result is of F simply says the magnitude of the force. That's all. But in case when it is written with a vector sign, see, few examples are listed here. The first example says the force is 100 Newton towards south. Second example says force is 100 Newton upwards. Force is 100 I cap Newton. Recall vector concept. 100 I cap Newton means it is 100 Newton and along I cap, direction of I cap. Or you can say in other words, it is force of 100 Newton and along positive x axis. Just recall, this is positive x axis, and along positive axis just we have taken a unit vector, define a unit vector as I cap. Okay, so any vector along x axis can be expressed in terms of I cap. 10 I cap means 10 Newton along positive x axis. 100 I cap means 100 Newton along positive x axis. See another example, minus 100 J cap Newton. J cap is along positive y axis, minus J cap along negative y axis. Then what is the meaning? 100 minus 100 J Newton means 100 Newton along minus J cap vector. Minus J cap means along negative y axis. It is along negative y axis. So this force along with vector sign, whenever we use, we have to express magnitude as well as direction. Okay. One point I want to discuss here for the Coulomb's law, that suppose there is a numerical question in which it is asked, calculate the force between the two charges. Listen carefully. Calculate the force between the two charges. When only force is mentioned, it means the question demands both magnitude and direction. You have to calculate force, means you have to calculate and mention what is the direction of that force or those forces. Okay, only one force definitely not there. If between two charges it is asked between two charges, so there are two forces. If it is clearly mentioned that find the force on charge q1, it means the question demands only one force. Okay, so what I have just said, that when the question asks calculate the force between two charges, then you have to calculate magnitude and mention the direction also. It is mandatory. Suppose in another question it is asked calculate the magnitude of the force. Okay, so we will use this formula only and magnitude is calculated. That is the answer of that question. It is not required here to mention the direction of that force also. You can write, but it is not asked in the question. I think the difference is clear. Okay. This is the last part of this video. Here one problem is there from NCERT 1.1 on page number 46. The question is, what is the force between two small charged spheres having charges of 2 into 10 to the power minus 7 coulomb and 3 into 10 to the power minus 7 coulomb placed 30 centimeter apart in air? Okay, here in this question the information is three informations are there. One is about the first charge, okay, and about the second charge and the distance between the charges. So what to do? Okay, you have to just put in the formula. You are having the formula F equals to K Q1 Q2 by R square. Then it is very simple. You have to just find out what is Q1 here, Q2 here, and what is R, right? Before going into before jumping into the calculation, first think about few points. One is regarding the unit. Okay, check whether the charges are in coulomb or not, right? If it is mentioned in micro coulomb, nano coulomb, then it is required you have to convert the charges in coulomb. You know the conversion, right? 1 microcoulomb is equal to 10 to the power minus 6 coulomb. 1 nanocoulomb is equal to 10 to the power minus 9 coulomb. Now check about the distance, whether it is mentioned in meter or not. If it is in meter, it's okay, simply put the value. If it is not in meter, suppose it is in centimeter. Right now in this problem also you can see that the distance is in centimeter. So what to do? First of all, you have to convert it in meter. Okay, one more point. If the distance is in centimeter, then what we prefer to write? Suppose the distance is 30 centimeter, so better to write 30 into 10 to the power minus 2. Always tries to calculate in terms of powers of 10. It minimizes your work, it simplifies your work. It becomes equal to 3 into 10 to the power minus 1 meter. You can also write it as 30 centimeter by 100 centimeter and it is equal to 0.3 meter. Okay, you can also use this one. Calculation will remain same, but I encourage you to calculate in terms of powers of 10 only. Where the work is simple, it's okay, but most of the time it saves your precious time during examinations. Okay, come on, let's move into the solution. First charge Q1, it is equal to 2 into 10 to the power minus 7 coulomb. Next charge is Q2, 3 into 10 to the power minus 7 coulomb, and the distance between them is R equals to 30 centimeter. I have taken it as 0.3 meter right now, but you have to write it as 3 into 10 to the power minus 1 meter. When the distance is in centimeter, just multiply it by 10 to the power minus 2. Okay, you know this thing. Now apply the formula. Okay, just put the values of K, Q1, Q2 and R. You will get the result. And now just try to remember what I have just said few minutes before. Come on, read out the question again. What is the force? Is our work is over, or still something it's remaining? We have to mention. Yes, magnitude is over, but question demands direction also, because the question is what is the force. If it is like what is the magnitude of the force, then it's okay, done, it is the answer. But we have to mention the direction also, right? So the magnitude of the force is written in word here. It is not required to write in words. Okay, just simply after the calculation you just mention here as answer, okay, in bracket. That's okay, no need to write in words. You can write, but it is not required. Okay, now you have to mention mention the direction. It is mandatory according to this problem here. Since the charges are of same nature, force between them will be positive. Force between them will be, sorry, repulsive, right? Force between them is repulsive. Okay, clear? So be careful while solving the problem, right? They are simple points, but they have to kept in mind always while solving the problems, right? Okay, uh, it's all for today, and the discussion will be continued. Thanks for watching.